In this lecture, what I want to do is kind of provide some further discussion about integration, just because I was worried I complicated things a little too much. So what I want to do is just give you some molecules and say, okay, a real problem that I could ask you is count the number of signals for both proton and carbon, and then for proton, count the determine or predict the integration for each signal. Okay, so let's do some examples. So and we'll keep this just a few. For each molecule, determine the number of signals, and we'll do 1H and 13C, along with the integration for each 1H signal. Okay, so if we had a few examples, let's pick on, just so you can kind of see the format, we'll do the one that we did in the last lecture. So in the last lecture, we determined that there were two 1H signals. And so we have HA, and there are HAs sort of everywhere. I'm going to have to redraw the molecule just so I can fit all of the labels with carbon. So over on this side, we have HB. So hopefully that's okay, that the A's and the B's are in the same, are in separate chemical environments, but there are a bunch of A's and a bunch of B's. So then for this one, I would say the integration for HA is equal to 9. HB is equal to 3. Okay, so the ratio of HA to HB experimentally is 3 to 1. There are 3 times as many HAs as there are to HBs. Now, if you were given the molecule and you wanted to just say, okay, what do I expect the integration to be? I would say, well, there are 9 HAs and 3 HBs. So the integral is 9 to 3. Now, experimentally, you don't get the number 9 and 3 when you actually do the experiment. You get a big peak for HA, a little peak for HB, and their relative areas after you divide by the greatest common denominator would be 3 to 1. So that is sort of what I was trying to go for when I talked about the integration. Let's do the C13 signals now, just because it's fresh in our mind. So we have this molecule, we would have Ca. Now, that's in the same chemical environment as these 3 carbons. And because they each have 3 hydrogens attached that are themselves in the same chemical environment, all of the HAs were in the same chemical environment. Now, Cb would be over here, and then we can't forget Cc. This is just one of those instances where we have a carbon that does not have any hydrogens present. So the number of C13 signals is actually, in this case, greater than the number of 1H signals. Now, it turns out that when you try to do an integration experiment, we could go ahead and like propose what the integration should be. That is that Ca should be 3 times bigger than Cb and Cc, but it doesn't work out that way experimentally for some reasons I'm not going to get into. It's called, it has to do with relaxation time. So you just don't do the integration experiment with carbon-13 NMR, so we don't worry about it except for proton NMR. Okay, some of the other molecules that we had been looking at were molecules like this. So here we have HA, HB, and HC. Now this carbon down here has an HA that's in the same chemical environment as that carbon pointing up, because by free rotation, we could rotate the molecules so that we could position those in identical chemical environments. So anytime you can achieve symmetry by free rotation, you will by free rotation, you will be in the same chemical environment. Okay, so we have HAs at those two positions, HC. Now for our carbons, we have Ca, which is in the same chemical environment as Ca down here. I'm going to go ahead and label this Cc just to be consistent with our previous example. Well, I guess I call it HB. So then we have Cb and then Cc, sure. So the number of 1H signals and C13 signals are both 3 in this case. Okay. Now, if we look at the integration, what we have to do is pick on each H signal by itself. So we have HA, HB, and HC. So the HA integration is actually 6 because there are 3 hydrogens on the first Ca and 3 hydrogens on the second Ca. So we have 6 H atoms for HA compared with 1 H atom for HB, and then C would actually have 3 H atoms. So the answer for the integration in this case is 6 to 1 to 3. If we divide by the greatest common whole number denominator amongst all of these, it's 1. So we have 6 to 1 to 3 ratio. If you just wanted to focus on HA and HC, you'd have a 2 to 1 ratio. But again, we should include all 3 of the signals for our hydrogen atoms. Let's do another example. Let's say we've got every college student's, well, not every college student, some college students' favorite, which is ethanol. So we have HA, 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 B, B, and C. So the number of 1H signals is equal to 2 or 3 because this HC may not count. We'll just let you be the judge, okay? I would say it probably won't see it. So if I had to like predict exactly how many signals I would see, I know that I will see 2. Sometimes I may see 3. So if you wrote 2, you're correct. If you wrote 3, I suppose you're correct. If you wrote 2 or 3, you're getting deep, and that's also correct. Okay, so 2 or 3. So for HA, the integral is 3. For HB, the integral is 2. I mean, for HC, 1 or NA. Now, you know, in all honesty, I will accept 1 or NA here, but in all honesty, it's probably not applicable. If you did observe it, it would be partially washed away by the solvent. And so you might get like half or something, like some number that doesn't really make sense. And that's because half of the hydrogens are washed away. And we'll get into that when we look at the solvent for an NMR spectroscopy experiment. Okay, so that is an addendum to integration. So hopefully that cleared things up for what you actually have to do on paper. I guess maybe I went a little bit too deep into the lab stuff. So anyway, we'll continue to pick up with NMR data in the next lecture.